Well, hello again, it's Cliff here from Down Under. In this video I'm going to talk about ball screws, hardened C7 ball screws, machining of them, checking them, and talking about housings, talking about machining in a center lathe, some tips and tricks for doing this type of work. This was quite challenging, machining these hardened screws, and there were a few issues and it took a bit longer than I anticipated. So if you're thinking of doing a CNC conversion, it would be worthwhile having a look at this video because it'll help to illustrate the type of problems that you or your machinist is likely to come up against. Alright, cheers. I've got a machining job to remachine the ends of a couple of ball screws. I thought to start with I'd just do a couple of basic checks to video document their accuracy. So I'm going to rotate the ball screw in the ball nut and do a couple of measurements. Let's just have a look at that now. So first off, the ball screw in the ball nut is quite a good fit. It's not rattling around in there. There's a bit of spring, but it's returning. So the ball screw and the ball nut have quite a good fit. I'm about 250 millimeters out from the center of the ball nut. Let's have a look at concentricity. So we're just past the zero there. Turn it quarter of a turn. We are about 5/100ths different there. Another quarter of a turn. A little less. A little less. So mostly we're running at about, yeah, that's about the extreme. We're about 5/100ths out of straightness. What this is doing is measuring the straightness of the ball screw and the thread that is ground, I suppose, on the ball screw of a run out of about out of straightness of about 5/100ths of a millimeter. Over 250 millimeters, that's about 2 thou. That's not too bad really. That's total run out. That's about 1 thou off center over that length. Seems reasonable to me. Alright, now let's check the concentricity or run out, if you like, of the machined end that is already on there. So let's come into contact with that diameter on 0. The play is very minimal, there's just a little bit of spring there. Okay, let's rotate it. Okay, we're getting a run out of just over 0.1 of a millimeter, nearly 11/100ths. That's about 4 thou run out in close. That's out of concentric. Let's move further away from there, and this will give us an idea of the angular alignment, the axial alignment of the axis angular alignment or misalignment. So it's worse there. So we have a concentricity error and a axial angular error, angular misalignment error. There it's at that distance out, what's that, about 40 millimeters out, we are now 15/100ths of a millimeter. That's about 6 thou. Okay, let's go a bit further. Let's see what that machined portion is. It looks like it's cylindrically ground, or perhaps turned and then polished, but I think it's cylindrically ground. We have an error there of about 0.2 of a millimeter. No, that's not quite on 0. 0.22 of a millimeter. 0.23 of a millimeter. So we're looking at 8-9 thou run out there. Yeah, that's starting to get up there, isn't it? That's not too good. So what that means is when the thrust bearings are tightened up at this point, they are not concentric or in angular alignment with the ball screw thread, and so they will be fighting each other and putting stress on the thrust bearings and on the ball nut. That last ball screw was 32 millimeters diameter. This ball screw is 20 millimeters diameter that I have to remachine the end on. So let's do some basic checks on that. So I've moved out only 150 millimeters from the smaller diameter screw to keep the proportions approximately similar. Alright, so let's check it for concentricity. I'm in contact there. Play is hard to measure now with the smaller diameter ball screw. I think that's mostly flex because it's returning to zero. So okay, we've got a zero reference there. Let's rotate it quarter of a turn, a couple of hundredths out, another quarter of a turn, coming back to zero, another quarter of a turn, a couple of hundredths out. That's pretty good. 150 mil out, it's about 3/100ths of a millimeter run out. That's just a bit over a thou. In total, that's just a bit over a half a thou off center. So, you know, that seems pretty similar to the other shaft, if not a little better. Okay, well, let's look at the concentricity of the other end. That's been machined. Now I don't know if this is machined by the manufacturer of the ball screw or whether there's some other machinist has done it subsequently. Let's bring it down into contact there, zero there, and we'll rotate it. Yeah, that's a lot more concentric than the 32 millimeter shaft, isn't it? We have a run out there of about 2 or 3/100ths. Let's come a bit further along, get some feel for axial angular error. Yeah, there's quite a bit more there, isn't there? We are 800ths already, and we're only about 25 millimeters along. That's quite a bit of axial angular error for that distance. So that's not good when you're running the thrust bearings on that diameter. It's going to be causing the ball screw to fight the rotation, and there'll be quite a bit of stress between the ball screw and nut and the thrust bearings there because of that axial angular misalignment. Just try it right on the end. See what it's like there. Just quickly. That's about 0.15, about 6 thou, but I've got a bit of flex coming into the equation now. If I carefully try and avoid that, about 0.13, about 5 thou run out there. Just talking with the customer about why there's this discrepancy in the quality between the ball screws and nuts and the machining on the end, and he thinks what it is that the ball screws and nuts are made in a plant that mass produces long lengths of ball screws, and then they are at a different premises machined on the ends and sold on eBay. So we have two different machinists, the production machinist that makes the ball screw and nuts, and the dealer in China that does the machining to spec and ships them off. So it looks like this will be the dealer that does the machining that is on the ends that is not so accurate. Here's some more information if that's helpful. These ball screws that I'm machining apparently are C7 grade. It's always interesting to do a bit of research. THK have got a lot of information online. I probably shouldn't go too much into all these details because there's so much information readily available online. But for example, a C7 grade is a rolled ball screw. It has a plus or minus of 50 microns. So that's about plus or minus 2 thou per 300 millimeters. So 50 microns per 300 millimeters is 2 thou per foot approximately. Yeah, so that's a pretty low grade of ball screw. The same grade is used in the Tormac 440, but the 1100 and the 770 use a higher precision P4 ball screw, which is a ground ball screw, to higher tolerances, and there's an allowance there of 6/10 per foot. That's, just over half a thou per foot versus 2 thou per foot on the C7. It's not easy to find information online for P4. The C system seems to be more common, and I think a P4 is approximately equivalent to a C3. We're getting about 11 microns over 300 or 400 millimeters, which is around about the rate of a P4 at 6/10 per foot. So it's probably something like a C3 compared with on the Tormacs 1100s and 770s, compared with a C7 for a rolled ball screw on the 440 and this job that I'm currently doing. It's really worth your while taking your time before you start to make machinist-friendly drawings. What do you call them in the States? Blueprints or plans or something? But anyway, drawings, dimension drawings that represent the work from a machinist point of view. That is all the dimensions from Z0 being the end of the work, and dimensioned that way from that datum, and all the diameters nice and convenient, because what you will get from the customer usually, or even a CAD modeler printing off a PDF, will usually be from the wrong datums, and you can easily get confused and make a mistake. It's really worthwhile converting it all over to machinist-friendly drawings, whether you're doing it on a manual lathe with digital readout or a CNC lathe with conversational programming. It really helps to have drawings set out in this way. It's worth taking 5 minutes to do that and familiarize yourself with the job much more intimately. Fully digest all of the proportions and sizes and fits and put them down in a way that you understand. That way you can concentrate on machining and not be getting confused about what is required. It's really worth spending the time doing that. On a clipboard, on a nail by the wall, in front of you on the lathe, or beside your digital readout, somewhere where you can keep glancing at it to check as you're machining, saves a lot of stress. So I need to set the ball screw up in the lathe to remachine the new diameters and lengths, and I can't go off the existing machine diameter to set it up because I know there's errors there. So I've got to base the setup off the actual ball screw, and so I've got a precision 3-jaw chuck that's been ground with a tool post grinder. If you're interested in that subject, have a look at my recent video, 3-jaw chuck accuracy, where I go into grinding the inside of the jaws in a way that displaces the jaws according to the work clamping forces and gets you good concentricity or run out and good radial and good axial angular alignment. And so the chuck's very accurate to start with. Then I put in some accurate aluminium parallels, and I can clamp down on the threads rather than risk damaging the threads with the crest of the threads with the hardened jaws. I'm just letting it deform into the aluminium, and I can set it up concentric by the following method. Well, these ball screw threads have double crests on them, and they're slightly different diameters. So I can set a dial indicator to just contact, go in to a decent depth, because we're checking for run out as well as angular alignment. Take a note down one end. You can see there on the dial indicator, this is a 1/100th dial indicator. Come down the other end. Check that's concentric and parallel in the different positions like that. And I can adjust the chuck because it floats on its back plate to get the concentricity, and I've just ground the chuck to get the axial angular accuracy there, and it's showing up as very parallel with this measurement. So I can now set the ball screw both concentric and parallel to the axis of the lathe. Then I'll put a center in the end just to stabilize the whole thing, and then machine the new diameters and threads. Well, that's a quick and easy way to set it up that gets it within half a thou or so over that length, and that's suitable for the class of machine that this will be going into, and the class of ball screw and nut that this is. But if you wanted extremely high accuracy, there'd be better ways of doing it. For example, you could machine up a heavy metal sleeve that was split, put that in the chuck, and then bore the ID until it's a close fit. So then when you bore it, you generate extreme accuracy both radially and axially. Then you could slip the ball screw into that machined bore and tighten it up with the chuck, and you would get very good accuracy then within tenths of a thou. And while I'm machining in a chuck to the finished dimensions here, I fully admit this is not the most accurate way to do it. Holding on the crest of a thread in a 3-jaw chuck will only get it reasonably accurate with great care. The optimum way would probably be to rough machine it like this, but leave a few thou on, then put centers in the end, then put it in a cylindrical grinder and machine the diameters between centers with the whole shaft rotating. And then you're going to generate very accurate parallelness, axial alignment, and concentricity. But not many of us have long cylindrical grinders with the correct setup. I've got a cylindrical grinder and I could grind one of the shafts in this way, but the other one is just too long for even my Brown and Sharp cylindrical grinder. So I've got to do one of them like this anyway. I might as well do them both. Here we are here with the cylindrical grinder, and you can see the problem. It's a fair size cylindrical grinder, but I can't put it between centers, this long shaft, and it won't go through the headstock, just too small a bore, and so I'm left with a universal jobbing shop lathe. So that might get you thinking, well, why don't you machine it between centers in a center lathe? You know, there's many different ways to skin a cat. Sure, you could do that. You could put centers in it with a driving dog down one end and machine it down this end, cut the thread and the diameters right down by the tailstock end, and you generate good accuracy there. But there are problems with doing it that way. You get a lot of torsional flex, and the driving of the part is very critical for screw cutting and rough machining, so there's problems there. So maybe you should only finish turn it like that, so then you should rough turn it close to size this way, then put it between centers, then finish turn it. That would be a better process, but obviously it would take a lot more time. So you're constantly weighing up different machining options and thinking about what is going to be the most time effective and give you the accuracy you require. So now that I've got the ball screw set up concentric in both radial and axial alignment, I'm going to put in a center. There's some good reasons for doing that. It allows me to use a rotating center to stabilize the part when I'm machining it, and also it gives me a reference center that allows me to check when I've finished machining that it is still concentric and can always go back to that position. We have a reference center. So I'll run the lathe now and you can get an idea of the errors in the end machining that I was talking about earlier on. You can see quite bad run out there in that diameter. Now we have a center in the end of the work, and it's very useful for stabilizing the work, and it provides a reference datum of the center line of the axis of the part. Well, this ball screw doesn't seem to be as hard as other ball screws I have machined. Tungsten carbide is machining it quite easily. Other ones I've machined was extremely borderline. Even with tungsten carbide. But I'm just taking light cuts to start with until I get through any case that may be there. Yeah, it feels tough, but not that hard. Maybe around 50 Rockwell C, something like that, if I was to guess. Well, that went well, all machined up to tolerance, and the nuts just a nice fit. It's a good idea to check that the center is still concentric when you're finished, because it tells you whether it's moved during machining or whether the steel has had any stresses that have let go, and you get some feel of how accurate the part is. And that's shifted very slightly. We've got a run out of about plus and minus 1/100th of a millimeter, which is not enough to worry about. Could have been a little bit of stress in the steel relaxing, but it's still pretty straight. Well, I'll just go into setting up the shaft, the 20mm shaft that I'm doing now, concentric, in a bit more detail. Now we're further into the video. A lot of you who are only vaguely interested will have dropped off. If you're still watching, you might be interested in the details, so I'll go into the details for you guys. So the chuck's held onto the back plate with 6 of these 8mm cap screws with a little bit of clearance on them, and 3 of them I put spring washers under, and those cap screws are just nipped up to the compression, half compressed spring washers. The other 3 cap screws are loose, so now it's just held by 3 spring washers, and I can easily make the adjustment. So come down one end, just checking you can see me okay, and come to the crest of the thread and turn it to the next spring loaded screw, to the crest of the thread, to the crest of the spread, and then on the high point of the screw, because the weight of the chuck is bearing down, it's easy. Oh, did I just bump it then? Hit it with a bit of copper or something like that and just give it a wee bump, and you just tap it down with the gravity of the chuck assisting you, and then come down the other end and check that you have angular alignment correct. Obviously we're not just worried about run out, we're worried about the angular alignment as well. So both ends of the screw is checked in 3 places, and I'm just getting it to within 1/100th of a millimeter. That's less than half a thou over that length for this grade of work. I don't want to be spending hours getting it to 1/10. That's a lot more accurate than it was, and within the sort of range of work that this will suit. Now I can adjust up the other cap screws that don't have spring washers under them. They don't need to be massively tight, because you've got to, you might be thinking, oh, but you haven't got it spigoted on. Don't forget, it's like a vise on a milling machine table. You've got a big diameter face that has a huge amount of frictional clamping over that diameter. And, you won't have any problems. You don't need to have that spigoted on. I mean, obviously there'll be some situations where you need to consider that. Everybody has to take responsibility for what they're doing, but I've found over the years in my own situation, speaking personally, that you don't need to have massive tension on those screws and that it never moves. Well, this 20mm shaft's becoming quite a challenge. I cut the end off, the previously machined portion off, and now I'm machining it down to different diameters. And you can see there, if you look at the surface finish, that the hardness is changing. It's quite soft down the tailstock end and becoming increasingly hard down the other end, getting up towards 60 Rockwell C, I would say. It's breaking down the tungsten carbide tooling, and so I'm having to sharpen the tool with each cut, and it's extremely borderline, and yet down the other end it's quite soft. So I'm thinking why, trying to reverse engineer why this is the case, and probably the machinist that takes the stock lengths of ball screw and machines the ends on them, tempers them at the end. Probably manually tempers them with a gas torch, heats them up hot enough, something like a 1045 steel probably, that's induction hardened, to perhaps 60 Rockwell C at the mill where the ball screws are rolled, but the machinist tempers the end to make it a doable job, tempers them right down to 30 Rockwell C, makes it easy to machine. So if you're going to do a job and machine an existing ball screw, you've got to think about this, that the actual ball screw itself is probably very hard and very difficult to machine. I can just do it with tungsten carbide. Ceramic would be better. It's an intermittent cut when you're machining the thread and very quickly breaks away the edge, so it's a difficult job. And when the machining loads become heavier, you've got to think about the work shifting and losing the accuracy of position that you've carefully set. And so you may have to reset the job after you've rough machined it. So this can become very time-consuming work, and you want to think twice about doing this work as a contract machinist to a low fixed price, because there's all sorts of unpredictable difficulties like this. I'm so glad I took the time to put a center in the end, because not only does a rotating center greatly stabilize the security of the part for rough machining, but it also provides a reference concentric diameter that you can use to check that the part hasn't shifted before you go on to do the finished machining. Well, that was a challenge. That was really tough to machine, and it took a lot longer than I had anticipated. These are the sort of real world problems that you're up against. So as hard as the hobs of hell in that last inch. Pretty borderline. I'm glad the thread wasn't down that end. But it's come out well, and I'm really pleased with it. Thanks for watching that video. On to a different subject. Some of you might be interested in this, so I'll put it in at the end of the video. I'm just machining a milling machine knee casting for a CNC conversion, and I'll put a few clips in now. And I'm setting it up to do some machining in this big old Chinese mill. And I just find accuracy a real joy. I'm just checking how vertical and parallel the back faces of the slideway, the Z slideway of the mill, using the Z slideway of this mill. And this is in hundredths of a millimeter. That's very good, isn't it? Over about 6 inches, it's only about 2/100ths of a millimeter out. That's pretty good considering the class of both of these machines are pretty budget, and there's so many variables that could throw a major error into that measurement. Alright, thanks for watching, guys. I hope you found something there useful. If you did, feel free to like and subscribe, and that might just encourage me to keep making these videos. Alrighty, see you next time. Cheers.